Okay, so I hope everyone here is here for a stats kind of review. I know this year many classes have done away with a final, and it's kind of all geared toward your final project, which is sometimes called like your capstone project. But all in all, it's this kind of project which combines everything that you've learned in stats together in one place. So that's kind of what we're here to review about. And I think one of the main parts to review is definitely on StatKey. So we can start with that. Is everyone okay with starting on StatKey? All right, so I'm going to share my screen. And we're just going to go through some general StatKey rules and how to set things up. So for your final project, you're going to be dealing with two means. So anywhere that you see a problem that says difference in means, that's where we're going to be starting. So you are going to have to do a confidence interval, which is also called a bootstrap. And then you're also going to be required to do a hypothesis test with all of the data that you collect. So let's start with the confidence interval. So we're going to go confidence interval for difference in means. And let's just say that this was your data right here. If you were to enter your data, you hit this edit data button. And see how it says M,15. So in this sample, it was males versus females. So to label them, we always have to line them up sort of like this, with if they were male or female or whatever two groups you decide on doing, and then comma and put the quantitative value, which is that number that you got for that specific person. And then the header row is just so you can keep track of which is which. So you could say gender versus, and then this one is exercise, like hours of exercising. So you would do gender, comma, exercise for this type of equation, and that's your header row. If you don't want to insert that in, you just uncheck this insert header row, and then after all your data is in, you hit OK. And you kind of see that there's nothing really on the plot right now, but it does show over here what your original sample is. So it says that we have the difference in our sample means, which is X bar 1 and X bar 2. So those are our notations for males and females in this survey. And see how we got this difference of 3. And where that 3 shows up is that's going to be right in the middle of your graph. So this 3 right here demonstrates this is where the peak of your data is going to be, right in this 3. And then these ends show your sample size values. So you know that in males, there's 20, and then in females, there's 30. So for your project, you should have, I think, 30 in each group. So this is just a way of checking before you actually plot your data points in your graph to make sure that all of the data is right. So you should have 30 and 30 for when you do your project. And then this dot plot here shows both data sets separated. So you can see on the top here, this is just for females. On the bottom, this is just for males. And if you hover over each one, you can see what the exact point is that they're trying to say. So this was males, and this person here exercised for 8 hours. And this dot up here was a female who exercised for 10 hours. So now what we do to create a bootstrap is we have to generate samples up here. And for most cases, you'll be generating anywhere between 1,000 and 3,000 samples. So I think it was 2 for the most part that you're generating. And this gives you data for basically what a bootstrap is think of it as all of your values are going into a hat, and you draw one of those values and you look at it, you record it on a plot like this, and then you put that value back into the hat. And then there's always that chance of drawing that number again. So what this shows is basically 2,000 times that we did that same procedure with the difference in these two means. So we just took our two samples and the difference between the two of them, and we ended up getting this nice bell-shaped curve. Now, in most cases, we are dealing with a 95% confidence interval. So in order to do that, you want to hit this two-tail button. And what that's going to do is that's going to show where our data is in relevance to our confidence interval right in the center. So see how this says 0.95? That means it's a 95% confidence interval. And then we would record our end caps right here and right here. So since this is males versus females, when we try to describe what's going on in this graph, and I'll explain more of it when I show you my example project. So how we explain it is we say something like, males exercise anywhere from 1.7 hours less to 7.592 hours more than females in this study, or for the population. This is what we're trying to predict will actually happen. So does everyone kind of understand how that works? Just gonna kind of scroll down. Okay. Does anyone have any questions on that or anything with the setup of getting your interval? Yeah, so down at the bottom here, these two values represent your interval. And then these two values up here are that's your p-value. With a two-tailed test, this is really important that you actually add the two together. So you're actually going to take this one and this one and add it together every time you have a two-tailed test. Because if you just take the p-value from this one, yes, we're recording that these dots, the red dots over here, that's relevant to our p-value, but then we also have to take into consideration on this side as well. So that's why we add those two values together. So that's going to give us our overall p-value. Or that's going to be our significance level. That's your significance level. So see how we have 95, basically that's 95%. So that means we have 5% significance on the sides there. Okay, so that's the basis of how to set up your confidence interval for the difference in means. And that is going to be one of the steps on your project, is to do something like that.
What are the numbers on the bottom again?
These numbers right here represent your interval. So when we would say something like this, usually if we were just dealing with one mean, like if we were just dealing with like females and number of hours exercised, we would say, we would kind of interpret it a little bit differently. But since we're comparing the two, and we're saying that X bar 1 in this case is males and X bar 2 is females. So that means we're saying the male part first, and we're saying that males exercise 1.7 hours less to 7.592 hours more than females. So this would just be like if you had a difference in means problem for your final. Let's say that you wanted to see different GPA scores or something between males and females. And if you have a negative and a positive number, it just means that the first group is this much less to this much more than the other group. Does that kind of make a little more sense?
Yeah.
Okay, cool. So,
Wait, so when you add those two together, Does that make the significance level or the p-value?
So in this case, I think this is, I think I was getting it confused with the hypotheses test. I think this is your significance level in this case. Yes, because when we add these two together, we get 0.05, which is basically the leftover percentage after doing your 95% confidence. So yeah, I think that would be your significance, but it could also be your p-value. Yeah, so I think in some ways it could also count for both. I'm just trying to think of what you would do. I'm sorry, I get kind of confused with StatKey sometimes because I forget like what one we're actually dealing with. So I think in this case, it would be your significance level, and then in another case, it would be your p-value, but I'll have to check back with that. It'll come to me, but I just can't think of it right now. Okay, so is everyone good with your confidence interval? So with that, we're going to move on to demonstrating a difference in means for a hypotheses test. So just like for the other one, we're going to go down to this difference in means. And here we have, we're going to edit our data. We're going to put whatever our factors are, whether it's male and female, or wears glasses, doesn't wear glasses, resident versus commuter, whatever the case may be, we're going to enter all of that data in and then put the value corresponding with that person that we took the data from. And then the same thing, this header row is only checked off if you label it at the top. So if we put gender versus GPA or something up top, then we would check off that header row. But if we delete that, then we actually uncheck this box. So we don't want it to have a header row. And then we hit OK. So now we can see that, again, this is that original sample. So these are all of our data points where they usually are. We can see here that the difference between the two means is 0.79. And then right over here, we can see that both sample sizes are equal in this case. So now what we're going to do is we're going to generate a couple thousand samples so we get a good rough estimate for our hypotheses test. And the one that you will be dealing with the most, I'm pretty sure, is a two-tailed test. So we're going to select that. And then here's where you would adjust your NCAPs. And what we do here is we're going to compare it to our original sample. So this one's a little bit different. So a confidence interval is usually centered at our original, which is this. It's usually centered what would be 0.79, but with these type of problems, we're actually centering it at 0 for a hypotheses test. So that's kind of how you know the difference between the two. So now what we do is we adjust this NCAP with our original sample, the difference between the two, which is that 0.79. So all we're going to do is we're going to come down here, we're going to type in 0.79 because that was our original sample. We want to test to see if it's going to be different from that value. And then this is where you're going to get that. See, I think this is the one where this represents the p-value. Because then what we would do is we would add these two numbers together and get a p-value to then try to conclude about your hypotheses. In all cases of your project, I think you are doing difference in means and you're doing you're testing to see if they're different. So you're not testing to see if one is greater than the other, one is less than the other. You're testing to see if they're different. So that's why I've always been selecting this two-tailed test, because that shows the difference in means. It splits up the graph and it has two areas for the p-value to lie. So when we add these two 0.029s together, then we get a p-value for that. And what we do then is compare that to our alpha value, which is 0.05. So that's kind of the standard alpha that we compare all of our p-values to. And the reason for that is that's usually what we compare a 95% confidence interval to. So we kind of just use it as a general estimate for most of our data. You can see here that this technically isn't 95% of the data in between, and that's totally fine to just leave it just as that. So the only thing that we adjust on the hypotheses test, which is this randomization test, is the end cap on which your original sample lied. So just like if this said negative 0.79, then we would adjust this one to negative 0.79. And then you see how our values would slightly differ if that were the case. It also will change a little bit more depending on how many samples you have to add. And I know I kind of did this at the beginning, you generate 1,000 samples. If you're ever just kind of like, wait, how many times did I click that? Like how many samples did I generate? You can see right here, it'll always tell you how many samples you generated. And see how this mean is also very, very close to 0. Like I said, the null is almost always going to be 0, and that's where we center our data right here. You can see there's actually a lot of points in this value for that. And then right here is your standard error or standard deviation. So that's going to be the space in between each of those dots roughly. Each of these points is going to be about 0.4. You can see it's not like totally, it's not exact, but it's a rough estimate for about what the standard error would be. And then this same thing, it would require some sort of explanation on what's going on here. So you would then put this graph, you would screenshot it or use that snipping tool and kind of put it on your document or wherever you're recording your project. And then what you would do is you would have to explain what's going on. So you would say that you conducted a hypotheses test for the difference in means, and this is what you found. This is where the p-value comes into play. So you would add these two values, which are your p-values, together, and you would compare it to that alpha value of 0.05. And then the little term that I like to use is that when p is low, we reject HO. So every time that you get a p-value less than that alpha of 0.05, you know you have enough evidence to reject your null hypothesis. And to refer to it, your null hypothesis is that the two means are equal. So your two means that you have could technically still be equal if you do not reject it. But if you reject it, then you're saying there's proof that they might not be the same in all of your experimentation. So does that, I know that was kind of a lot, does that make sense a little more? Any questions on that?
So after, like, let's say p-value was low when you reject it, what conclusion does that draw?
Right, so when we make our conclusion, let's say in this case, I'm just gonna do the math here. So it's 0.027 plus 0.027. So we've got 0.054, which is actually slightly larger than the alpha value. So we would not reject HO in this case. And that's when we would write our sentence similar to how we would write a sentence for our confidence interval. But instead of saying like we are 95% confident, we would say we have statistically significant evidence or we do not have statistically significant evidence that there is a difference between the two means that we found. And the way to tell if there's a difference or not is if you reject or do not reject. So if you do not reject, we don't have evidence. But then if we do reject, then that means we do have evidence.
I have another quick question.
Yeah.
So I know in the case when you are rejecting, or no, when you are not rejecting H naught, it's not saying that HA is true or not. It's just simply inconclusive. Would there still be methods that we'll have to consider in order to come up with at least some sort of conclusion?
So you're saying if you conclude like we do not reject H naught?
Yeah, because I know that basically says that our test results are more inconclusive. We're not saying that something is true or not in that case.
Right. So basically how I would conclude it here is I would say we do not have statistically significant evidence against the null because we can't really support the alternative if we found that that p-value is higher. So in that case, we would kind of say just that, like kind of explain the reasoning behind it. And that would just be saying that our p-value is greater than our alpha value, and that every time that the p is greater than alpha, we would not reject HO because we don't have enough evidence against it. So we don't necessarily accept the null, we just don't reject it. Does that kind of make sense?
Yeah, so then when it comes to the case with the RIN report, we'll just have to say that it's inconclusive, like we haven't really came up with an actual sort of conclusion.
Right, so our alternative would kind of be set aside because we didn't really prove that it is possible. So yeah, in that sense, it would kind of be not necessarily inconclusive, but it would be some sort of, we wouldn't be able to tell if there was a difference, because in some cases in this study, we may have found that the means are actually equal. And that's why we do not reject it, is because we're saying that in our null, the two means are equal. And if this graph yields anything that says that the means could be equal, then we really don't have any evidence against the null. So we go with it and we say, you know, P was higher than alpha and we just don't have enough evidence.
Makes sense. Thank you.
Okay, yeah, no problem. Any other questions? And then thinking next, if it's okay, I will share my project so you can kind of see like a rough draft of what it might look like. So mine was conducted, I think, last year around this same time. So the structure and the look of it might be a little bit different. So don't think that you have to do all of the work that I did, because, you know, it might be sort of a different setup for different classes and different professors have a different way of putting it out. So I will just share that. So I'm not sure if you guys have like an introduction part, but this is just basically what is said with your question. What are you trying to find? So are you trying to find the difference between male and female GPAs? Are you trying to find how many siblings one has versus if they wear glasses or not? You know, you can come up with, you can kind of have fun with it too. You can say, you would have to pick a categorical value, which is something like male, female, resident or commuter, online versus in person for most of the semester. Those are kind of some topics that you can play around with and try to get an estimate for. And then you have to pick a quantitative value, which is something that you can take the average of. So whether that's GPA or SAT score, number of siblings you have, number of hours of sleep you get a night, something on the lines of that. I did mine, it was males versus females on how many apps they have on their phone. And this was the data that I got from this. So you're going to need like some sort of table that shows this information. So these were my 30 females, and these were the 30 male students that I had asked. And these were the numbers that they gave me for how many apps that they each had on their phone. So how I would do it is when you're keeping track of your data, maybe even start by making a column like this. I did mine actually right on loose leaf paper. I think I actually have it with me, yes. So this is kind of how I did it. It was like this kind of sheet of paper that it's all folded up and everything, because I just carried it around with me and I asked people, I mean, this is when we were still allowed to like be on campus and interact a lot, but I would just carry it around and ask people, you know, how many apps do you have on your phone? Do you mind helping me with a survey real quick? So that's kind of what I did to the extent of it. You will definitely get a lot of numbers. It may seem a little intimidating to try to get 30 people for each category. I think it's still 30 for most of you, but I believe that you guys can do it, and it's not like you're asking a really hard question. Like if you ask how many hours of sleep do you get a night, they should pretty much know. And then you just have to mark down whatever your two categories are, whether it's females and males, or wears glasses, doesn't wear glasses, resident versus commuter student, any two kind of categories that you would pick. And then over here is what are called descriptive statistics. And this is where I just put what the averages were for each of them. So I got the average of female number of apps they had on their phone to be about 68.5. And then for males, 70.9. And then these are just more of these statistics. You find these by going into your calculator and doing, I think it's one var stats. Okay, yeah, I see. So some of you were actually given a data set. I just found out. So whether you have to actually go out and take a survey or you're actually working with a data set already, the setup for this kind of chart is pretty much the same. This is just to show all of the data that you picked, and then to show what, basically using that data, what does it show for the rest of it here. So there's the mean, median, mode, standard deviation, the minimum, the maximum. This is going back to, I think this was like chapters 1 and 2. So you can kind of see how this project is pretty much a gathering of everything that we've learned in stats and applying it to one group of, actually 2 groups of people. So then there's all that. And then of course on the bottom, we do the difference between the 2 means. So we gathered our mean here and here, and then somewhere on the sheet, depending on the setup, that's when you do the difference in them. And this value, this 2.4, that was the negative 2.4, that was a pretty big value for the whole project to have that difference. And then this was just displaying the data differently. Again, I'm not really sure because all your projects are a little bit different. But you'll probably need some sort of descriptive statistics like this, either in a dot plot, a histogram, or a box plot to demonstrate your data. This one's a little hard to see, but this is males versus females right here. Again, this is males on the bottom, females up here, and again here. So those in StatKey, I can show how to get to those. So let me show that. So we want to go to the sampling distributions here. We're going to go to mean, or no, wait. Is it there? These. So one quantitative and one categorical variable. Then this is going to give that information that I was just showing you. So again, you go to edit data, you enter all of your values into here, making sure to have that comma break in between them. I strongly suggest when you're writing your data out to actually save all of your values like this into a Word document. So that way, every time you need to enter more data in, you can just go to that Word document, copy the whole list, and paste it right back into StatKey for each of these different things that you have to do, whether it was this or the confidence interval or the hypotheses test. So after you put all your data in, it's originally going to give you a dot plot. And then on the side here, this says all of your descriptive statistics, just like the ones that I wrote down in my plot there. And this actually gives all the information right here. These are the means for each of them. And then actually this overall category averages these together. So you really won't need that, but you will definitely need these means, the standard deviations, the sample sizes. And then it's going to give you first in a dot plot, and then you can scroll across the top here. This is going to display the same information as a histogram and the same information as a dot plot, or a box plot. So even if this data, even if these certain graphs aren't required, sometimes they're good to look at with your data, just so you kind of get a feel for what your data actually looks like. Like if it's left skewed, if it's right skewed. Like this data set is very, very right skewed. So that means a lot of the values are on the lower end than the higher end of whatever the data set may be. Same thing with the dot plot. You can kind of see that a lot of the values are on the lower end and there's only a few on the higher end. The box plot is the really important one because this one will actually show your outliers in this case. So it'll actually demonstrate and describe where the outliers are. But you still have to follow the outlier formula in order to solve for them if that is part of your project. But at least this just kind of gives you a virtual kind of representation of what your data looks like with the outliers here. So does that all make sense? Good. Okay. So let's go back to projects so I can show you a little bit more. So we have those. And then this is where we put those different graphs in that we worked with earlier. So this is the bootstrap confidence interval. And we're always going to be working in difference and means. And then this is what I was saying with kind of interpreting it, saying what's going on in the graph. I know sometimes before it was just kind of like pasting the graph on, but in most cases your project will require some sort of explanation or a couple sentences on just what do we know and what does this graph show us. So according to this interval, it shows this 95%, and it's the 95% of the data is between these 2 points, but it means that the number of apps for females will be between 16.583 less, that's this number right here, to 12.7 more. And the reason we write less and more is because this one over here is a negative number and this one is a positive. So that's key for difference in means. We definitely want to see if there's a negative, we don't just say the interval lies between -16 to 12, we want to say that the first group is this much less to this much more than the second group. Does that make sense? Okay, and then this last sentence is also really important. Since 0 is in the interval, it could mean that the two population means could be equal. And this one is a really big thing to recognize. So when 0 is in the interval, that's a big thing, because when we're looking at the difference in means, and we say the difference between the two means is 0, that's saying that the means are the same. So let's say the difference in mean I got for one of the data points was 3, and then the other one I also got for 3. So then that means 3 minus 3 is 0. And that means that they could be the same. And in that case, we really don't have evidence that they could not be equal because of that 0 being there. Is everyone okay with that? Okay. And then the next one, this is that randomization distribution. And sometimes, depending on what your values are, they might look a little bit different on where you put your data in. So again, you just kind of describe what's going on in the graph. You describe what is being shown, what are you testing. You can even include something like this is a two-tailed test between the two means. The sample size is this. You kind of just include that into your description. And then, yeah, so this is actually the one where we wouldn't necessarily say we're 95% confident about something. This would just say if we have statistically significant evidence, or maybe we don't have statistically significant evidence about something that happened. So then going down here, then this confidence interval I actually did on my calculator. And the reason why is because this is just to reiterate, again, this is a different way of showing a confidence interval. This isn't necessarily like the other one, where this is a bootstrap confidence interval, where this one is just using that one calculator function, this 2 sample t interval, and then showing what goes along with that. In this case, to put it on your calculator, I know a lot of the times we actually work in stats when we enter our data in, but in this case, we're gonna actually switch that to data. And that's when we use the L1 and the L2 list. And again, when we're writing these descriptions, it's almost better if you try to write a little bit more about what's happening than not enough. So even here, I said that, I labeled the 2 lists, L1 and L2. L1 was for females, L2 was for males. And then I explained what's going on up here. I said this was the interval, so it was between 17.83 less to 13.025 more. So females had this many less to this many more apps than males. And then right here, this is where the test can become inconclusive. And this goes again with that 0 being in the interval. So when that 0 is there, we really can't conclude it. And that only happens if 0 is there. And again, that goes back to thinking if we have a mean of 3 and the other mean is also 3, then they minus out and they're going to be 0. And that's really not proving against the null, because the null says that mu1 equals mu2. But if we get values that mu1 is 3 and mu2 is also 3, then they are equal. And we don't have enough evidence against that. So that's why, when we say inconclusive, we kind of have to back that up by saying that 0 is in the interval, and that's the reason why. And then this is another one, a hypotheses test for the difference in means. This one, you're going to go to this 2-sample t-test to conduct. And this is just your steps that you can, like your steps that you write down for doing something like this. And I don't know if the steps have really changed a little bit, but I kind of learned it like this, where you state your hypotheses, and then you state what you do in your calculator or what you're going to do in StatKey. You state your p-value, you say whether you reject or do not reject, and then your conclusion sentence. And in this case, I had a high p-value of this 0.75 number. So when we have that high p-value, we know that we don't reject HO. We don't reject HO. Only when p is low do we reject HO. So this is saying that we do not have statistically significant evidence showing that there's a difference in the population mean between your two groups. For me, it was cell phone apps between male and females, but maybe it's number of hours of sleep you get a night between residents and commuters. Something on the lines of that. Or if you have one that's already set up for you, I know some classes are using the Census Bureau, which you would get data off of that and use it, but I know other classes might be doing the kind of going out and taking a survey. But yeah, and then sometimes you'll have a conclusion right at the end, and you say, if you met the goal, which was to prove the hypotheses wrong, and basically wrap it up from there. And you say, after doing all of these tests, did you find evidence that there was a difference? Did 0 always come up in your interval in every test that you did? So, and then you always wrap it up with the p-value that you obtained for the different problems. And then from there, you kind of make your big decision. So you've made all of these other decisions along the way with these different tests and intervals, but then you come together and you make that final decision at the end, whether you have evidence against the null or you don't have evidence against the null. And I know this may seem like a lot, and it is, and it's because I think this is actually in some cases in place of your final exam. So your final would usually incorporate everything that you've learned in stats kind of together all in one exam. And that's kind of what the project does too, is it kind of takes together everything that we've learned and just applied it to one big project about a data set. And you kind of see how you can pretty much do everything that we've learned in stats and apply it right there. So are there any questions about the project?
I have another question.
Yeah.
So for the written report, is there a certain page limit that comes with it, or is it not really that restricted?
I don't think, it kind of depends on your professor. So I know for mine, I think it just mattered that you had all of your information. And as long as you explained all of your graphs well enough, or to the extent that your professor would want you to explain them, then that's kind of how you would get full credit. So as long as you include all of your graphs, you just, you include your graphs, you kind of explain what's happening. As far as page numbers, they might say specifically like on page 1, that's your intro, on page 2, that's where you put all of your data points, and then page 3, that's the test, and then the interval, etc. So it just kind of depends on how each professor sets up the actual project, but as long as you just have all of your data in there at some point. And each of your descriptions, they don't necessarily have to be so long. It just kind of has to be long enough to explain what's going on in your graph and what conclusion could you make off of that graph alone. Okay, so any other questions? Okay, so I'm seeing in the chat, if we have problems with the project, is there anyone we can contact for help? So definitely contact the professor first and see what they say. If there's like a specific question on, if it's a specific question on the project, they should be able to help you, maybe guide you through it and show you how to do it. As far as anyone else, I'm not really sure, but definitely I would think maybe asking classmates if, you know, how they set up a certain test and see if you set it up the same way, or but yeah, I would strongly suggest definitely emailing your professor first, or even setting up a Zoom call. So even in that, like during their office hours, I know it's kind of all online, so it's a little different, but if you set it up where you can meet, and then you could even share your screen with them so they can see your work and kind of help you out from there. So if that is all for tonight, I wish you guys good luck on your stats projects. And like I said, feel free to email me if you have a quick question about anything. Just let me know. And hope you guys have a great night, great weekend, and I wish you all the best of luck on finals and your stats project.